Hello everyone and welcome to chapter number 4, video number 2 in the 3-phase induction machine course. In the previous video we covered some tests to determine the motor parameters. Here in this video we are going to continue looking for no-load test and blocked rotor test. Let us start by the no-load test. In the no-load test we are going to run the machine at no load, but we need to recall the equivalent circuit of the 3-phase induction motor. So this one is the first approximate equivalent circuit, and in the no-load test we are going to disconnect the machine from any mechanical load, so the rotor shaft is rotating by a speed close to the synchronous speed. So that one is close to the synchronous speed. In this case S equals 0 or close to 0, and consequently our rotor over S will be very high value, or we can say open circuit. If this one is open circuit, so I rotor equals 0, and the equivalent circuit of the machine at this case will be this branch, which is R core parallel to XM. So the purpose of this test is to determine R core and XM. So what is the procedure to determine R core and XM? To determine R core and XM, we need to measure the no-load voltage, which is usually the rated voltage of the machine, the no-load current, and no-load power. So to measure the no-load power, we need to have a wattmeter. So because the machine is balanced and symmetrical, so we can have one wattmeter and multiply this reading by 3. Alternatively, we can use 2 wattmeter method. So what is what 2 wattmeter method? We're going to have 2 wattmeters connected as we see here in the figure. So if that one is phase A, that one is phase B, and that one is phase C. So the current coil of the wattmeter here is measuring IA and measuring the voltage VAB. And this wattmeter is going to measure the current coil IC, and the potential coil is going to measure VCB. And this ammeter is going to measure IB, and that one is going to measure VAB. So he didn't tell us how this 2 wattmeter is going to measure 3-phase power. I'm going to explain that one in a later slide. But now, when we're going to have the reading, the no-load power P equals P node 1 plus P node 2. So we record the values. But sometimes in the lab, if we're going to use a wattmeter like this one, we are going to find the reading of wattmeter number 1, PO1. We're going to find this pointer is going to deflect in the other side here. So this means that one need to be corrected, and the result of that one should be subtracted, not added. So if I change the current coil or potential coil, so the pointer is going the other side, and in this case, power no load equals minus PO1 plus PO2. So let's go for the analysis. No-load test mathematical analysis. From previous slides, we know the equivalent circuit at no load, where R core and XM are parallel to the supply voltage. At no load case, usually we apply the supply voltage at the rated value. So I'm going to convert all the values recorded from the test to phase values, not line values. As we can see here, we have the phasor diagram V node phase value. I core is in phase with the voltage V node, the current in the resistance R core, and the current in the magnetizing reactance XM is lagging the voltage by 90 degrees, as we can see here. I node equals I core minus JIM, and the no-load current is lagging the voltage by angle phi node, and I plotted this phasor diagram deliberately where I core is smaller than IM because the no-load power factor is bad power factor in the range of 0.1 to 0.4. So the circuit in this case is more inductive. So how are we going to make the analysis? We are going to record the no-load power. Whatever the wattmeter number 1 is going to measure, positive or negative, we have P node. So using phase values, P node equals 3 V node I node cosine phi node. From this equation we can determine cosine phi node, where cosine phi node equals P node over 3 V node I node. Once we know cosine phi node, we can determine I core, make a projection for I node in X and Y direction. So I core equals I node cosine phi node, and IM equals I node sine phi node. So using Ohm's law, R core equals V node over I core, and XM equals V node over IM. Returning to the 2 wattmeter methods, there are 2 questions here. Question number 1, how can 2 wattmeters measure the 3-phase power? And question number 2, why does one of them sometimes show a negative value? So we are going to start this one by plotting the phasor diagram for the three-phase system. We have VA, phase voltage, VB, VC, they are shifted 120 degrees. And the current for the no-load circuit is lagging the voltage by angle theta. And this angle is close to 90 degrees, 70, 75, 80, 85, it depends. And this is why I plot the current is very far from the voltage here. So that one is close to 90 degrees. So the current IA with a value I, which should be I node, right? That one is lagging the voltage by angle theta. And definitely IB is shifted from IA by 120 degrees and IC is shifted from IB by another 120 degrees. Regarding the line voltage, VAB equals root 3, the phase voltage, root 3V, and leading the voltage by 30 degrees as we can see here. So definitely VBC, that one will be a voltage here, root 3V as well, and this angle is 30 degrees, and then we are going to have VCB 180 degrees from that one. Turn back to this circuit, so we have here phase A, phase B, phase C. So the current here for wattmeter number 1 is IA and the voltage is VAB. And for the wattmeter number 2, the current is IC and the voltage is VCB. So we are going to start by wattmeter number 1, measuring the power PO1. So that one equals the voltage VAB multiplied by the current IA, cosine the angle between them, which is theta plus 30 degrees. So we are going to substitute by the values VAB and IA, and then we're going to use the trigonometric identities to expand cosine theta plus 30. So that one equals root 3V I cosine 30 cosine theta minus sine 30 sine theta. So let's simplify this expression. So that one will be root 3VI root 3 over 2 cosine theta minus half sine theta. We are going to distribute the voltage magnitude and current to the cosine and sine. So that one equals 3 over 2 VI cosine theta minus root 3 over 2 VI sine theta. Regarding wattmeter number 2, the voltage is VCB, which is the same amplitude, root 3V, and the current is IC with the same amplitude I, but cosine the angle between them, which is theta minus 30 in this case. So this is the angle between them, which is theta minus 30. So use the same procedure. We have root 3VI cosine minus 30 cosine theta minus sine minus 30 sine theta. Cosine minus 30 is cosine 30. Sine minus 30 is minus sine 30. So simplifying this expression, that one will be root 3VI root 3 over 2 cosine theta plus 1 over 2 sine theta. So the final form will be 3 over 2 VI cosine theta plus root 3 over 2 VI sine theta. Add PO1 and PO2 together. So that one is going to cancel this expression and this expression. So the the final answer is 3 VI cosine theta, which is a three-phase power we know. So the 2 wattmeter method, we can say that the power at no load equals PO1 plus PO2. It depends on PO1 sign. So that one might read positive or negative. So you answered the first question, why 2 wattmeters or how 2 wattmeters can measure three-phase power. But why one of them is measuring negative value? So I'm going to focus on PO1. Look here for the angle theta plus 30 degrees. So cosine theta plus 30 degrees. So if, for example, theta is something like 80, so 80 plus 30, so that one is more than 90 degrees, and in this case cosine is negative. So wattmeter number 1 is going to measure negative. To make sure that wattmeter number 1 is reading positive, this theta should be lower than 60 degrees. So if, just in case, a no load angle or the angle between the voltage and current something like 55, so that one is going to measure something like cosine 85, and that one is positive, so you can add PO1 to PO2. But if the angle is close to 90, as we can see here, definitely PO1 is going to measure a negative value, so we are going to subtract that one from PO2. So what about PO2? So here cosine theta minus 30, if we take the same numbers, so 80 minus 30, so that one cosine 50, so that one is definitely positive. So this is why we have one of the wattmeters measuring negative value. So if that one is going to measure negative, or the pointer is going to deflect on the other side, you are going to change either the current coil or the voltage coil and take the reading by a negative. And then you are going to have PO2 positive, and then you are going to find P node or the no load power. Let's take some facts and comments from the Noload test. Noload test is performed at rated voltage and frequency. And at no load, the machine is running close to the synchronous speed, so the slip is close to zero or almost zero. The no load current is in the range of 20 to 40% of the full load current. The machine operates at very low power factor under no load conditions, typically the range of 0.1 to 0.4 lagging. These facts and comments give you an idea that you did the test and you have correct results. The machine operates at a highly inductive load at this time because we have R core and XM, and R core is almost 2 to 10 times greater than the magnetizing reactance, so the circuit is highly inductive because the current here in the magnetizing reactance will be higher than the current in the core resistance. And that one is explaining why the power factor is close to zero. The no-load power represents core loss plus rotational loss. So we know that core loss is voltage dependent, so core loss is proportional to voltage square. If we have the current going through our core, so that one, or the power loss in the core, will be V square over R core. So the core loss is proportional to the square of the voltage, and rotational loss is speed dependent. If the speed is constant, the rotational loss is constant. So the question now, we measured from this test P node. So how we can separate core loss from rotational loss? From the Noload test, we measured P node at rated voltage and frequency. If we have the lab facility, we can make a simple test to measure the no-load loss at different voltages. So we are going to measure the no-load power at 80%, 60%, 40% from the rated voltage. So can we have at 20%? I didn't expect that you can reach up to 20% because the condition here, you need to ensure that the machine is operating close to the synchronous speed or equal to the synchronous speed for each reading. So if you cannot reach 40%, you are going to stop at 50%. So we are going to record the values, voltage and no-load power for each reading. Then we are going to plot a curve like this one, where x-axis will be the voltage square and the y-axis will be the no-load power. So that one at 100%, we measured that one from the previous test, and now we measured at 80%, 60%, 40%. So if we extrapolate between these points, we can reach at 0 voltage. We have a power here, that one is rotational loss. So we know that rotational loss is speed dependent, while core loss is voltage dependent. So if the voltage is 0, so the power here is pure rotational loss. So how we are going to calculate the core loss now? So returning back to this point, we are going to substitute for the no-load power equals rotational loss plus core loss. But if you are going to use the exact equivalent circuit, you might need to add stator copper loss, which is 3I node square R stator. But if you are going to use approximate equivalent circuit, you are going to cancel this part. So no-load power at 100% from the voltage or rated voltage equals core loss, which is unknown now. Rotational loss we calculated from this part, so we can calculate the core loss. Now we can separate between core loss and rotational loss. If you don't have the lab facility, you can use empirical formula here that rotational loss is assumed to be third of the no-load power and core loss is assumed to be 2/3 of the no-load power at rated voltage. We are still with the no-load test, and the no-load test can help us to determine the motor inertia. So why you need the motor inertia? If you like to have a dynamic simulation for the three-phase induction motor, we need to know the moment of inertia. We're going to see that one in chapter number 5, next chapter, when we're going to simulate this machine using MATLAB Simulink. So let's start by the torque equation. Torque, electromagnetic torque minus mechanical torque or load torque equals J, the moment of inertia, multiplied by the angular acceleration alpha. Alpha equals the rate of change of speed with respect to time. There are many tests can be performed to determine the moment of inertia, something like retardation test or deceleration test. Here I'm going to list one test, which is the deceleration test, for sake of simplicity. So the test tells us that we are going to disconnect any mechanical load from the machine. We are going to leave the machine to run freely. We're going to apply the nominal voltage, the rated voltage and frequency, and the machine is running close to the synchronous speed. Suddenly, we are going to cut off the power supply. So let's look here. So the machine is running by the synchronous speed, and at 0 time, we're going to count this time, we're going to disconnect the supply. We need to record the speed versus time. So for a machine with low inertia, we have here the blue line or the blue curve, and with a machine with high inertia, we have the red curve. So we are going to record that one using tachometer or shaft encoder. If you don't have any of those, you are going to use a stopwatch to record the time that the machine stops completely. For the high inertia machine, you are going to have this one, we'll call it that one T stop. Let's say that one T stop 2. For the low inertia machine, that one could be T stop 1. So now how we are going to determine the inertia? So let's look for that one. J equals T friction over alpha, because torque load is 0 now. So T friction over alpha gives you J. So how to determine T friction? From the Noload test, we have the Noload power and we have the rated speed. So we can say that T friction equals P node over omega rated. And this is how the Noload test is going to help us to determine the J. So we need to determine T friction. Either you measure that one or you are going to measure the no-load power over omega rated, you can determine T friction. What about alpha? To determine alpha, you need to use this speed time curve. So alpha equals omega 2 minus omega 1 over T2 minus T1. So for example, if we take this machine, so that one we can say omega 1 and that one is omega 2. So that one could be T2 and that one could be T1. So you are going to take omega 2 minus omega 1 over T2 minus T1. So that one is the slope of this curve. If you don't have this curve, you are going to calculate the speed omega over the stop time. So that one can give you an idea about the inertia. So once you determine alpha, so J equals T friction over alpha. Now it's time to look for the last test, blocked rotor test. So far, we finished the turns ratio test to determine the turns ratio between the stator and rotor, the DC test to determine R stator, and the Noload test to determine R core and XM. And from this test, we can determine the moment of inertia, and we can separate between rotational loss and core loss. Blocked rotor test is used to determine R rotor and leakage reactances X stator and X rotor. But before we start the analysis and procedure, some people like to call it locked rotor test, and other people like to call it short circuit test because the machine will be at standstill. So that one is similar to the short circuit test of the transformer. But the most common used words are blocked and locked. So here I'm going to use blocked. So when we are going to run this test, we are going to apply a voltage and we try to stop this shaft from any movement. So in this case, NR equals 0. And when R equals 0, S equals 1. And in this case, the equivalent circuit test 2, we have this part as if we have a short circuit. And we have the impedance will be R stator plus R rotor over 1 plus J X stator plus X rotor. Both V blocked and I blocked are phase values. So what is the procedure? The first step, make sure that the rotor is held stationary, either using heavy load torque or any external means, something like a clamp or a wooden piece. That time, the motor or the shaft is at standstill and the slip equals 1. And we have the equivalent circuit as we can see here. Then we are going to apply supply voltage, three-phase supply voltage. Increase this voltage gradually and keep an eye on this ammeter until this ammeter reaches the rated current or full load current of this machine. We are going to record the voltage, power, and current. Then we are going to have all the tests, all what we need for the test to make the analysis. Again, this test can be performed using 1 watt meter and you're going to multiply by 3 or 3 watt meters, but here I'm going to use 2 watt meter method similar to the Noload test. So we measured here P node, which is P node 1 plus P node 2, and we measured V blocked and I blocked. So how to make the analysis? From the previous slide, we measured B blocked, V blocked, I blocked. B blocked equals the reading of wattmeter number 1 plus the reading of wattmeter number 2. If the wattmeter number 1 is going to measure negative value, we are going to consider the sign as we did in the Noload test. B blocked equals 3 I blocked square R equivalent. So all the power is consumed in these two resistances. So R equivalent in this case equals B blocked over 3 I blocked square, which is R stator plus R rotor. So what is the impedance of this network? So V blocked over I blocked, definitely phase values. So we determine Z equivalent. So Z equivalent equals R equivalent plus JX equivalent. And from this one, we can determine X equivalent, which equals root Z equivalent square minus R equivalent square. But we need our rotor, X leakage stator, X leakage rotor. So from the DC test, we know R stator. So we can use this equation, that's R rotor equals R equivalent minus R stator. If we don't have any information about the DC test, or the DC test measurement is not available, so we can use this assumption that R stator equals R rotor equals R equivalent over 2. Also, a valid assumption that X stator equals X rotor equals X equivalent over 2. So now we determined all the parameters of the machine. R stator, R rotor, R core, XM, X leakage stator, and X leakage rotor. Also, we can determine the rotational loss and core loss and the moment of inertia. Similar to the Noload test, we are going to highlight some facts and comments about the blocked rotor test. So the first one, we are going to apply reduced voltage to the stator in this test. So gradually increase the supply voltage until you reach full load current or lower value rather than full load current to avoid any damage to the motor or overheating. And because the test is sensitive to the current in this case, so prolonged testing is not accepted to avoid any overheating, so it's recommended to measure voltage, current, and power as quickly as possible. Another point, the blocked rotor test is usually performed at low frequency. You didn't highlight that one in the analysis or the procedure. Yes, I'm going to highlight that one here. Typically 10 to 25% of the rated frequency is used for the blocked rotor test. And for the motor designed for 50 Hz or 60 Hz supply, it is recommended to have 10 to 15 Hz for the test. Why that one? And if I used 50 Hz, for example, is that wrong? So let's look why we need lower frequency. When you are going to work for higher frequency, the reactance will dominate the results. We don't like to have any domination from the reactance. We need to focus more on the rotor resistance. Also, that one is going to simulate the actual slip conditions. So when the machine is running at full load, the slip will be something like 3%, 4%, 5%. So we need to be close to the actual case. Also, it's recommended by IEEE standard 112 and IEC standards that running these tests should be at lower frequency testing if needed. So if you don't have the facility in the lab, so you can run these tests at 50 Hz. But for more accurate results, we should run these tests for lower frequency. I presume now that we are ready for examples. What will I watch in video number 3? In video number 3, we are going to cover examples about machine testing. See you in the next video.